So since we last spoke at the last capital raise, there's been some developments in the organization that we're going to give an update on. But first, thanks for Lewis Utting and the team that's developed a new slide deck for us that's really snazzy. Very impressed with it. And so before we go into the update, we've got ambitions and aspirations to expand our deep epitaxial solvent technology into not only battery recycling, but also metal hydroxide precipitate, e-waste, etc. So we're very impressed with the deep epitaxial solvent technology, and participating or pursuing those other markets really gives us a much broader exposure to a total addressable market. So it's worth explaining a little bit about deep epitaxial solvents. So deep epitaxial solvents being cleaner, greener, and more cost-effective than conventional methods of recovering metals. In terms of Iondrive and our advantage, we've got a very supportive and high-quality shareholder base. The market opportunities for us are massive, and we'll get a little bit into that. The technology that we've got has been proven at scale. The challenge for us, now that the chemistry has been proven into scale, is the engineering on how to make it work in a process, and that's the purpose of the pilot plant. We've completed the economic modeling, which is very compelling, and pursuing our early mover advantage, and we've got a clear path to commercialization. So looking at deep epitaxial solvents, just a little bit of background there. As context, deep epitaxial solvents are formed as an ionic liquid when you combine two solvents, both with high melting points, and that combination of the two, one a proton donor and the other one a proton acceptor, results in a much lower melting point. So your energy efficiency is so much higher. And just quickly to illustrate how these deep epitaxial solvents work, if we look at our application where we use it to separate cobalt and nickel very, very effectively, whereas other processes don't. And the reason is that cobalt and nickel are right next to each other on the periodic table, and they follow each other through a conventional process. And what the deep epitaxial solvent does is you can tune it so that one component of the ionic liquid binds to the liquid, to the nickel, dissolves it, whereas the cobalt will still stay in its solid form, and that's how you separate it. So very, very neat technology, and you can tune your deep epitaxial solvents to separate a range of metal groups. So for example, if you want to penetrate the waste market with different metals like palladium, platinum, gold, etc., we would tune our deep epitaxial solvents to very specifically and selectively leach out those metal groups. In terms of how we compare with other technologies, specifically in battery recycling, is the old conventional way is pyrometallurgy, where you effectively burn away all of the material and you're left with the metal alloys. Hydrometallurgy is where you use, for example, very strong acids to dissolve all of the material, and then you precipitate out the metals also as an alloy, but as a salt. And our process with the deep epitaxial solvents in a closed loop process does that selective removal of the target metal groups in a closed loop process. So once the solvents have extracted the metals, they're then recovered and recycled, and you can use the deep epitaxial solvents over and over. And the really neat thing about these deep epitaxial solvents is that they are benign organic materials. And in fact, one of the components that we use, choline chloride, is actually a chicken feed. It's a supplement. It's a vitamin. So all our organic solvents are biodegradable. So that's a really competitive advantage for us from an environmental point of view. So getting back to an update on where we are, this slide shows the top half as the commercial development and what's planned for the next 3 to 9 months. And then the bottom section is the technology developments. So we've completed the economic modeling through a third party, and we'll look at those results soon. And then on the technology side, the capital raise was for developing a pilot plant with an aim of commissioning and operating it at the end of the year. And so we've started with that work. We've done what we call stage one, which is the commissioning of the semi-continuous work. And we've started with the experiments there. So that semi-continuous work is to develop and optimize the process parameters that will go into the design of a fully integrated continuous pilot plant. So really important work that's taking place right now. We're progressing with strategic collaborations in Europe with a view on that consortium of industry partners across the entire value chain, or the value circle, as they call it, to establish a battery recycling industry for Europe. And then we're progressing with other application areas for the depictic solvents. First, starting with metal hydroxide precipitates, which is an intermediate product before it gets converted into precursor cathode active materials. So, for example, there's an interesting company in the US that's developed a recycling process that develops these MHPs as a product. And we've had conversations with them last year in using their product as a feedstock for our process to very selectively remove that nickel and cobalt and convert to PCAM materials. Then there's the non-dilutive funding opportunities, so specifically the grants that we've applied for within Europe and Australia. And then in the next 3 months, we want to have completed the design phase of the pilot plant that will commence after final investment decision to the construction and commissioning of a pilot plant. We've also got a program earmarked for University of Adelaide with an e-waste project, so a second another application that we've been pursuing. And those are the immediate milestones that we've got in our eyesight. Some results from the economic modeling is a bit of a mouthful to go through here. The first thing to explain is you'd see on the black mass throughput that we've got two values there at 21,000 ton per annum throughput, and then in brackets 10,000 tons per annum. So the explanation there is that the 10,000 tons black mass is a pre-treated black mass. So that's where we've removed all of the impurities, which are mostly graphite, which makes up more than half of your black mass, and other impurities that interfere with the process like iron, aluminium, and copper. So that's how we land on 10,000 tons of pre-treated black mass. We've developed a pre-treatment process that does all of that, and the raw black mass that feeds into the pre-treatment process comprises then 21,000 tons per annum. So that's just some of the numbers on our mass balance. We've used a 10% discount rate in the economic modeling, which was performed by an independent third party in Perth called Model Answer. And at that 10% discount rate, we end up with a very attractive NPV of almost 250 million Australian dollar and a 17.5% IRR. Both of those values are post-tax. Now, if we look at the sensitivities on the bottom right, let me just get my pointer going here. On the bottom right, we've got sensitivities for an NPV. And you can see by far the biggest driver of sensitivity is metals pricing. So the assumptions that we've made for metals pricing was based on Benchmark Minerals International. We engaged them to do pricing forecasts for us out to 2035. So these values are their projected values. If there's an upswing in metals pricing, it's got a huge benefit for the process. We're very confident in the numbers that they've now presented. I was at a BMI conference yesterday where we had an in-depth discussion and presentations from various people about lithium, nickel, cobalt, and manganese pricing forecasts, and which dovetail very well with their forecasted data. So there's a lot of confidence, not only in metals pricing, but also in the whole energy transition globally. I think a key message from there was that there's a lot of noise that's picked up in the media or accentuated, amplified in the media. So, for example, if Germany's electric vehicle sales are down, that's amplified as the whole of Europe's EV sales are down. That's actually not the case. The whole of Europe's EV sales are incredibly strong, above 35% growth per annum. Germany's got it's an enigma in that it's got its own problems with its automotive industry that has led to the downturn in EV sales. So I just mentioned that the conference showed very strong confidence in the numbers of where these metals are growing, which are linked to EV sales, and there's strong confidence in EV sales. And then on the middle graph there, we've got the sensitivities on IRR, and again, metal pricing is very dominant. Thanks, Jay. Some further assumptions here is these NPV and economic modeling calculations were performed over a 20-year operation period, which results in 5.8 years payback period. And this is a repeat of a slide that we had at the capital raise presentation, where we looked at our comparisons in this space. In the bottom section, we've got Ascend Elements. In the middle, Scilab, and then Decycle. All three of these companies are spin-outs from universities. And on the y-axis, the primary y-axis, we've got investments that were made in the companies in Australian dollar. So, and then on the secondary axis, one can see the market valuation after those investments. Now, the key thing to understand here is that they're all relevant to us in terms of battery recycling for Ascend Elements and Scilab. Decycle is a company that uses deep epitaxial solvents for e-waste metals and recovery. So that's the first thing. And then the second thing is that all these companies had a significant re-rating in their market valuation after successful pilot plant startups. So, as I mentioned earlier, the chemistry scales, we've shown that from small scale to large scale. The challenge is to convert that chemistry into a continuous process that you'd find in a commercial operation. That is difficult. So there's a really good reason why these companies have revalued so significantly once their pilot plants have been proven successful. And then just at the top here, just a comparison in terms of Iondrive and comparable companies in terms of market and valuation. So Iondrive sits at around 25 million. We've got MTM that sits at 100 million. They use a flash Joule heating process for critical mineral extraction. And they've got a pilot plant that's being constructed this year. And then is on the IPX that we can talk a lot about. That's had a transition from Australia to the US, a dual listing on the NASDAQ. And really interesting story on how they've grown their market cap in early stage with a lot of marketing, a lot of letters of intent signed with the end customers, and a number of other reasons that we're looking closely at in terms of following a similar trajectory. I think everybody's quite familiar with this slide. It's just showing how the share price has moved over the last almost 12 months. So the market cap now, as of yesterday, was 27 million. Interestingly, when I looked at this graph over Christmas, New Year, there was quite a rise in the share price, and it reminded me of my days as a young engineer on plants when we would ramp up the production, and management would come back and say, what happened? And we said, well, we didn't have management to interfere with production figures, so maybe you should all go more on holiday. The teams, so I often say we're blessed with a very, very competent and strong board. Michael, the chairperson, with Jack, Andrew, Adam, and recently joined Hugo with us. Myself, Ray, and Lewis, various experience in small cap companies and growing that technology. So a really, really strong team that's got experience on the technology side as well as the market side and how to grow organizations and capital raise experience. Just a bit of context again on why we're in metals recycling and how we do it. So the why is this market volumes that are growing significantly, or they're forecasted to grow significantly over the next 10, 20 years, all driven by the energy transition, so the uptake of electric vehicles. Those batteries come to an end of life. They can't be landfilled. They've got lots of value in recycling. So huge exponential growth in the market. The other thing to understand is that when these batteries come to end of life, they shred it into black mass, and more than 80% of that black mass is then shipped back to China, where the metals are recovered and turned into batteries again. So with the rest of the world being caught when the tide went out, with China leading the energy transition and producing more than 80% of the world's batteries, and COVID showing how critical access to the supply chains are, and discovering that China has sewn up all of the supply chains of these critical minerals, and an option for them, for Europe and USA specifically, and Australia, to have access to those critical minerals is to recycle these batteries. So that's driving battery recycling in Europe and the US, as well as all of the legislative and regulatory tailwinds in terms of ensuring that the black mass is recycled in Europe. Just a quick slide here on our process. So we take in the black mass, and we very selectively strip out the lithium, nickel, cobalt, and manganese as carbonate in the case of lithium, and then hydroxides for nickel and manganese, and cobalt as an oxide. And the second aspect that we're looking at, starting with business case development, is converting those battery-grade materials into PCAM. Now, the significance of PCAM is that in the whole of Europe, we've got a foothold, and where we want to establish our first market. In the whole of Europe, there's not one PCAM manufacturer. So that's another massive opportunity for Iondrive. We've got very good skills and access to skills and knowledge within Australia in technology that was developed at Perth up to a very large pilot plant scale. So we're very confident that if we want to extrapolate into the PCAM market, we can rapidly do that with very quick scale up. This is our business model. So this is the value circle that I spoke about earlier. So the end-of-life batteries are collected and then shredded into the black mass. Our primary focus is to convert that black mass into the battery-grade materials, and then the secondary focus is into that PCAM material. So just illustrating here, underscoring why we want to do this. Typically, black mass sells on the market for $2,000 a ton. On aggregate, those metal battery-grade materials that we produce retail for $8,000 a ton, and then the PCAM sells for $20,000 a ton. So there's a significant valorization that takes place. So that's our business model. And in terms of our commercialization pathway and our growth pathway, what's really interesting to understand here is if we look at the blue vertical bars at the bottom, that represents the volume growth in black mass. So that's when these batteries come to the end of life. And if we look at our pathway, where we're launching the pilot plant this year, followed by the demonstration scale plant, we'd be hitting a commercial plant right in time for when these black mass volumes come on market in serious numbers. And just quickly, a refresher on the pre-feasibility study that we completed last year. It showed that we're technically feasible and not commercially viable with economic modeling that's been done. Also, the industry partnerships that we've established within Europe and wanting to duplicate the same in the US, that has led to high confidence in progressing to a pilot plant stage and then using that as a platform to commercialize going forward.